So here we are in Chapter 3 already. Time sure flies when we're having fun, doesn't it? Chapter 3 is titled Basic Data Communication Technology. So last chapter we looked at basic data communication concepts, and so now we're going to take a look at some of the technologies involved in data communications. A lot of what we talk about in this chapter deals with what's going on at the physical layer. That is to say, the conversion of the bits, the zeros and the ones, into electrical and light pulses. So some of the things that you should be aware of as far as the physical layer is concerned is that it's responsible for establishing, maintaining, and terminating any of the physical connections between communication devices. Also, this is where we transmit and receive streams of bits. There is no data recognition here at the physical layer. Remember in the previous chapter we talked about encapsulation and how headers were put on packets and datagrams, that kind of thing. But here it's just all zeros and ones, and so the physical layer doesn't really read it as information at all, other than, what's the next bit? Is it a 0 or is it a 1? Operation is controlled by protocols that define the electrical, mechanical, and procedural specifications for data transmission. Even though wireless networks are quite popular these days, and of course optical, fiber optic networks as well, still the majority of network installations are copper-based. They're using wires to make the connections between all of the devices. So one of the important things to understand right off the bat is the American Wire Gauge Standard, or AWG. Think of electrons flowing down a copper wire like water flowing through a water pipe. So in other words, the bigger or the thicker that the wire is, the more electrons it can carry. So the American Wire Gauge Standard, or AWG, or AWG, is used to measure the thickness of a wire. The higher the gauge number is, the thinner the wire is going to be. So 22 gauge is much thinner wire than is 14 gauge wire. Another big concept that you need to understand with regards to electrical-based networks is the concept of attenuation. That is, as the signal travels down the wire, it decreases in power the further it gets away from the sending device. And so we talked about this a little bit in the previous chapter about the signal to noise ratio. So as that signal degrades, that means that it's closer to the same impact of the noise, the outside interference that's also occurring on that wire. And so it gets to a point where the receiving device just could not discern between the original signal and the noise or interference that's occurring on that wire. So this process of it decreasing as it travels down the wire is referred to as attenuation. And in most networks, especially the media types that we use, the different types of cabling, we talk about their attenuation point. In other words, how far the signal can travel before it degrades so much that it couldn't possibly be processed. So that's a very important concept to understand. And of course the other bullet, the sub-bullet point here too, which is that signal will also degrade faster when it's on a thinner wire. So thicker wires, we can travel greater distances with a good clean signal than we can on thinner wires. Now this interference that we've been talking about, one type of interference is known as next or near end crosstalk. This is where the signal that's traveling down one wire is interfering with the signal that's on another wire. So if we've got a pair of wires, which usually the way that electrical communications works is that you have one wire that's your ground wire and the other wire is actually carrying the signal. So they always operate in pairs. So one pair is going to be your transmitting pair and the other pair is going to be your receiving pair. So they can actually cause interference with each other, and that's what near end crosstalk is, or next. And so one way of preventing that is by twisting the pairs. So you'll notice when you create a patch cable and you strip away the outer sheathing of that patch cable, that the pairs inside are twisted together. And the more twists there are per inch, the more prevention there is against this near-end crosstalk. The other aspect of the signal-to-noise ratio that you need to be aware of is that how it's measured. And it's measured in dB or decibels. That's how we measure sound. And so the higher dB value that we have, that means that we have a greater signal to that of the noise that is occurring on the line. There are lots of types of media that are used to connect devices together within networks. As I said, still many of them are copper-based, but also we find that we're getting more and more into fiber optic network environments, and then wireless as well. And so in the case of a copper-based network, then the copper wire is the media that connects the devices together. And in the case of a fiber optic network, the fiber optic cable is the media that connects the devices together. And in a wireless network, it's actually the air between the devices that carries the radio waves that is the media in that particular case. So we're going to look at several types of media. First, we'll take a look at non-twisted pair, which is flat phone wire. If you've ever seen the old phone cabling, it was kind of a flat. It came in many different colors. I'm going to say flat gray, but it actually came in like a tan too, and black. But anyway, it was a flat cable. And then the more modernly used cable in most networks these days, at least in copper-based networks, is unshielded twisted pair, or UTP cable. There's also a shielded twisted pair, or STP, which is used primarily in IBM token ring networks. And before we started using UTP, unshielded twisted pair, many networks used coaxial cable. And there's two different types of coaxial cable. We'll talk about both thin net and thick net. And then again, the more modern type of media to use in the modern day networks would be fiber optic cable. So unshielded twisted pair cabling is the most commonly used type of cabling in data communications today. So UTP, as it's also known, is basically 8 pairs, or I should say 4 pairs, 8 wires total. And they're insulated copper. They're twisted in pairs, and the twists are anywhere from 2 to 12 twists per foot, and it's the twisting then that is used to actually reduce interference between the pairs and keep any outside sources of interference from causing data errors. The individually twisted pairs then are grouped together, covered with a plastic or a vinyl jacket, also known as a sheath. There are 7 different categories of UTP cabling. 3 of them are currently defined in the EIA-TIA 568B specification. And the EIA-TIA 568B specifies the topology, which is the way the cables get connected together to form networks, the cable types, the connector types that are going to be used in what is known as an EIA-TIA 568B compliant wiring scheme. Now, part of that wiring scheme also identifies the minimum performance specifications for the cabling, the connectors and components such as wall plates, also punch-down blocks, and patch panels that would be used in EIA-TIA 568B compliant installations. If you look at Belden's website or Siemens' website, which are cable manufacturers, you'll see that there is a specification 7, category 7, that they're currently working on. But as you'll see in the table that we have coming up here, only categories 3, 5E, and 6 are actually only currently recognized by the EIA-TIA. This is a good graphic here. It shows you a cross-section of 2 different types of UTP cable. Standard UTP on the left and screened UTP on the right. The only difference is you'll notice if you look at the screened UTP cable on the right, there is an additional cable shield, so kind of a thin shielding just inside of the sheathing that wraps around all of the 4 pairs of wires. So you can get in these cross sections, you can get a good glimpse of the makeup of a cable. So again, 4 pairs, 8 total wires. You'll notice that each color has a solid color and a white. It's half the color and then white. So usually we call that, like in the case of the blue, we call it a blue and a blue-white, orange-white. So just ways of designating, of course, the individual wires within the pairs. And of course they have copper center cores to them, and then all bundled up inside of an outer sheathing. The graphic at the very bottom there shows you some Cat5e, which the copper wiring, by the way, is AUG24. Remember, AUG is the American wire gauge standard. That's the actual thickness of the copper wire. And so again, you can see in that bottom graphic the twisting of the pairs together there. So there's 4 pairs twisted together, and again, total 8 wires. So this is the chart that I was talking about. You can see the categories for each of the different types of UTP cable there on the left-hand side. Category 1, 2, 3, 4, 5, 5E, 6. And as I mentioned in the last slide, there is also a 7 that currently hasn't been officially released yet, the specification for it. And you'll notice that in the category column, I have marked in red the 3 that are currently defined in the EIA-TIA 568B specification. So that's category 3 cabling, which basically transfers data at 16 megabits per second, used in older 10 base T networks, and tested for attenuation and near end crosstalk up to 16 megahertz. So the speed at which the data travels down the wire is also going to affect attenuation, as well as, remember, the distance, how far the data has to transfer or be transported. And then category 5E is what's most commonly used today, that will transfer data at 100 megabits per second by using 2 pairs, and with 4 pairs the specification allows for up to 1 gigabit per second. The speed on that is 100 megahertz, and generally used in fast Ethernet networks, also in ATM and gigabit Ethernet networks. And there is a little bit higher quality of control standard with regards to category 5E than there is in category 5 cabling. So it's better off these days. I don't know if you can even buy category 5 anymore. I think most companies are selling you category 5E. Category 6, you can see, will give you even higher speeds, 2.5 gigabits using 2 pairs, and based on the specification, it allows for potentially up to 10 gigabits per second using 4 pairs. So attenuation there is 200 megahertz, and this is a little bit more expensive wire, a little bit more difficult to deal with, but it's currently the fastest copper-based cabling that is utilized in data communications. Now, one of the things that you'll be doing in skills number 1 is you're going to build a patch cable. And so here's a couple of things to think about as far as common UTP installation mistakes. The main one is, the first one here will affect you as far as building your cable, and that's the untwisting of the UTP wire more than a maximum of 13 millimeters. So you don't want to untwist the wire too much, because remember, the twisting is what helps to prevent interference in that near-end crosstalk. So you only want to untwist the wires just enough so that you can fit them inside of the RJ45 jack that you're going to slip on. And of course we'll demonstrate that to you when we get together to do the actual Skills 1 assignment. One of the other common installation mistakes is that when you run bundles of cabling, a lot of times IT professionals and cablers will wrap those bundles in zip ties, and so if you pull too tight on a zip tie, you can actually cause the wires to be wound too tightly next to each other, and get some interference going there. Another problem too is if you take that bundle and you bend it too far. If you're trying to squeeze it in somewhere and you say you like bend it in half and it's really, again, tightly grouped together, that can cause some interference problems as well. Another type of cabling we don't see a lot of is shielded twisted pair, or STP. This type of cabling is much more expensive than UTP cabling. Was used a lot in the IBM networking environments, the token ring environments. So in this particular case of STP, the original cable was faster than was the original UTP. So that's why the first bullet here talks about the transmission speed being improved by the fact that it has additional shielding around each pairs of wires in addition to the entire group of twisted pairs. The shielding was metallic foil or copper braiding, and again commonly used in token ring networks and more expensive than UTP cable. So again, here's a graphic, good representation, cross-section of two different types of STP, standard STP on the left and screened STP on the right. Again, the screening is just like it was in UTP. It has that additional shielding, the cable shield, just inside of the sheathing. And so in this graphic, in both the left-hand or the right-hand graphic, you can see there's also an additional circle around the pairs of wires. So that's the additional shielding for the STP cable, and that's why it's called shielded twisted pair cabling. Depending on whether you have cable TV at your house or not, you may or may not have seen coaxial cable before. Coaxial cable many times is referred to, in fact, as cable TV cable. It has specialized insulators, shielding, separating the conductors. There's a solid, we'll see this in the graphic coming up, so I'll explain it when we get there. There's a solid copper core with like a fiberglass shielding around it, and then you have the outside braiding, which is the ground. It's capable of high-speed data transmissions over relatively long distances, and it does come in various thicknesses. In Ethernet networks, we've used two different types of coaxial cable in the past, thick net cabling and thin net cabling. In fact, thick net was often referred to as the solid or frozen yellow garden hose. It was very thick. I think it was like 0.5 centimeters in diameter as far as the copper core. And then the thin net was used, the thick net was basically backbone, so it would go like between buildings or between rooms, and then thin net was used to actually connect the computers to some sort of a hub, and then the hub was attached using vampire taps, they called it, to the thick net cabling that again ran between the rooms or the buildings. It says modern local area networks don't really use much in the way of coaxial cabling. That's true in the sense that the networks themselves don't use it, but of course cable TV now offers internet services, and so your modem that will connect you to your internet service provider, which in this case would be the cable company, is going to use a coaxial cable. Internally, you'll probably use Cat5e. So here's that graphic of the coaxial cable, and all coaxial cable is built like this, so regardless of what the thickness of the cable is. So at the very center, again, we have this solid metal inner core, and then there's an insulator, usually fiberglass or plastic, that's wrapped, or I guess it's actually molded, you could say, around that inner core. And then there's a foil shielding then on the outside, and that then is wrapped in this braided shielding, which is the outer conductor, which is usually the ground in the cable system. And then of course all wrapped together in a plastic or a vinyl jacket. These fiber optic cable is becoming much more prominent. Certainly when we're talking about reliability and performance and security, fiber optic is the champion in all three of those areas. Now, fiber optic is the most expensive media choice that's currently available, and it does deliver transmission speeds that are measured in gigabits, billions of characters per second, and it can also go over great distances, miles. As I mentioned in the last slide, fiber optic cable is the most secure of all the media that we've talked about because it's virtually untappable. Copper media is very easy to tap into, but fiber optic cable is very difficult to tap into. And the other thing about fiber too is it is immune to electromagnetic interference. So if you run it by an air conditioner or some sort of a large motor within a building, then that's not going to interfere with the data transmission that's occurring on fiber optic cabling. And so here's a graphic to represent fiber optic cabling. And so here's a graphic to represent fiber optic cabling. And so here's a graphic to represent fiber optic cabling. And again, these come in various thicknesses, but they're all pretty much made up the same. So at the very center we have a glass core, which you can see by the table down at the bottom underneath the graphic. It comes in various thicknesses of which are measured in microns. So that's the diameter of the glass core that you're seeing there. And then around the glass core is the glass cladding, which actually at the center of that glass cladding has reflective properties, and so that makes sure that the pulses of light that are traveling down the glass core remain in the glass core and don't get dispersed out from the glass core and outside of the cable. In addition to varying thicknesses within the wire, within the I should say fiber optic cabling, there's two different types of fiber optic cabling, which is multi-mode and single mode. Multi-mode allows us to, and is probably more common in most networks, allows us to basically connect devices to switches within a local area network, and single mode usually is so that we can travel greater distances, again between rooms or between buildings. And I think I failed to mention that, of course, outside of the glass cladding there is again a plastic or a vinyl jacket, very much the same as we see in the UTP and STP cabling. The bullet at the bottom is a good thing to remember. Fiber optic cabling does require careful handling. You can bend the fiber optic cable too much so that prevents the smooth flow of the electric, or I should say the light pulses through the glass core. Here's some more information on fiber optic cabling. This deals with the light transmission modes. We just talked about multi-mode and single-mode fiber. And so as the pulse of light is entering into that core, that glass core that we were talking about in the fiber optic cable, it's going to behave differently depending on the physical characteristics of the core and the cladding and the entire makeup of the fiber optic cable. So in the multi-mode type of cabling that we were talking about, it actually allows for multiple rays, and the rays of light then will bounce off the cladding at different angles. So that's why you can have actually multiple rays traveling down that fiber optic core at the same time. One of the things about having multiple rays, though, is that it can cause distortion, and that limits then the overall transmission capabilities of the fiber. So that's why with multi-mode it's capable of high bandwidth transmissions because we're having the ability to transmit multiple rays, but it does reduce the distance that the data can travel. One of your higher grade multi-mode cables is multi-mode graded index fiber. And in this type of cable, what they do is they actually decrease the refractive characteristic of the core. And so the reflected rays then are focused along the core more efficiently, so you don't get as much distortion occurring, so you get higher bandwidth, and it can travel at a little bit greater distance then at that point. So again, the type of fiber optic cable is again a higher grade, and it's known as multi-mode graded index fiber. So this is a good table here to refer to so that you can remember some of the properties about all these different cabling types that we've talked about. So it goes through some of the lower level categories of the UTP cable, and also covers STP, covers coaxial, and fiber optics. And so you'll notice that it has an AKA column here, also known as, gives you the bandwidth values, gives you the distance limits, and the different connector types that are used in conjunction with those types of cables. And there's a few comments about the cabling and its applications. And on the far right then, it identifies the most commonly used Ethernet network architectures that type of cabling is used in. So that would include Ethernet, fast Ethernet, gigabit Ethernet, and ATM networks. So now that we've finished talking about the different media types, we'll move on to talking about transmission technologies. The first is point-to-point data transmission technologies, which is probably the most common data communications method used to directly connect two devices. This type of connection can also be used to connect a computer to a peripheral device, like a modem or a printer, and operating at layer 1, which is the physical layer of the OSI network model. These technologies provide a physical connection that can be used to carry many higher level protocols, because the higher level protocols are occurring at the upper levels of the OSI model. And so the serial transmission standards are the most commonly used point-to-point data transmission techniques. There are several different serial communication standards that are available for uses. RS-232, USB, and IEEE 1394, or FireWire. RS-232 is one of the first serial standards that was implemented in computer communications, and it's actually still the most commonly used serial standard for modem communications. They use it also a lot in robotics, to have the computer systems talk to different robotic systems. Commonly it is referred to as a serial port. It's limited to 20 kilobits per second as far as its data transmission rate, and the distance is very limited as well, only 50 feet. Most commonly it's implemented using a DB25 or a Db9 connector, and we'll show you a graphic of what they look like. So I'm guessing that some of you maybe have never seen these types of connectors, since USB has been quite prevalent in the modern era of data communications. But again, we're talking about the RS-232 standard, which is used for communicating information between two devices. And believe it or not, even though we have all these pins here in these connectors, it is still serial communications. In other words, we don't have different pieces of data, different streams of data that's actually being carried over each of these pins here. The pins themselves were used to control the flow of the data and initiate the setup connection as far as getting ready to transmit the data and things of that nature. And there's actually only a couple of pins that were used in here for the transmission of the data itself. So two different types of connector, again, the DB25 and the DB9. And they call it a D, by the way, if you look very closely at the outer shell, the metal that's surrounding the pins there, it's kind of in the shape of a D. So that's called a D shell connector, and then whatever the number of pins are inside of that makes up the numeric value there. So DB25 on the left, and notice that's a male connector as opposed to a female connector that we see on the right there. So this graphic is a good example of what I was just talking about, how each of these pins in the 25 and 9-pin connectors is not actually carrying an individual stream of data, but instead most of the pins are being used to actually control the communication process between the two devices. So if you look at the left-hand graphic, the 25-pin graphic there, if you go down under the pin column, you'll see that pin number 2 is used for transmitting the data, and pin number 3 is used for receiving the data. And then I'll point out too, pin 1 is the actual ground. But all the rest of the pins there are actually used for some sort of a signaling process between the two devices and don't carry data at all. And the same is true in the 9-pin connector. One is used for carrier detection, meaning that we have a flow of electricity between the two devices. And then 2 is used for receiving data, and 3 is used for transmitting data, but then all of the rest of the pins are used for some other purpose, not to actually carry the data itself. So if you go back to that previous slide and you look at the graphic, you'll notice that on the 25-pin connector, one pin represents the DCE channel and another pin represents the DTE channel. And in the communication process between two devices, one device is responsible for the timing of the message. This is synchronous communications that's going on here in this RS-232 circuit. And so what that means is that one device has to define what frequency we're operating at. If you remember back to the graphic that we looked at that had the sine wave, and we were talking about frequency modulation, and we said how we can alter the length of that sine wave. Well, that length obviously is going to affect the length of time that the device that's receiving the electrical pulse has to wait to determine whether that pulse is a 1 or a 0. So the two devices, on both ends of the communication, they have to agree to what that frequency rate is going to be, because if they're operating at two different frequency rates, then one machine could send, say, 2 1s in the time that another machine thinks that it's only received 1 bit, 1 1. So anyway, one end of the communication process is always set up as the data communications equipment, or the DCE, and it's the end that has the actual clock to create the synchronization of that communication process. And so it's important for you to know which end is which. And so the DCE, again, is the clock end. It generates the synchronization. And if we're talking about connection to a modem, it would be the end of the cable that connects to the modem. The DTE is kind of like a slave. It's just going to operate at whatever the speed is that's established by the clock end, by the DCE end. And so again, in a case of connecting a cable to a modem, there's the DTE end is going to be the one that actually connects to the terminal, to the computer itself, the computer's 25-pin or 9-pin port. One other aspect of RS-232 is that if you're looking at two ends of a cable, the left end of the cable, pin 1, if you follow that wire all the way to the other end, to the right end of the cable, it's still going to be pin 1 on the other end. So that's one of the properties of RS-232 that's different than the EIA-TIA 568 wiring scheme that we were talking about earlier. In EIA-TIA 568, the send pin, or the send wire on one end of the cable, ends up being the receive wire on the other end of the cable. So it's not a straight through type of arrangement. So RS-232, it is straight through. All the pins on the left end, whatever number they are on the left end of the cable, they're the exact same number on the right end of the cable. We also talked earlier about the difference between parallel communications and serial communications, the fact that your computer operates generally using parallel communications, and then between devices usually we use serial communications. So when the computer wants to send data from this parallel organized data system, where we have multiple paths of data that want to be sent out a single path of data. Obviously, you've got a lot more data coming in from the computer that can be then output over the serial line. So in the communications component, whatever that happens to be, the modem, network cards, this particular technology, I believe, is only applicable in the modem environment. The modem uses a Uart, Universal Asynchronous Receiver Transmitter, and it's basically a buffer. Think of a Uart as a buffer. So as all this data comes in very quickly from the computer side of things, and it's trickling out slower on the serial side of things, then the Uart is the buffer that can hold all the incoming data and then properly flow it out to the serial port using the modem device. So as it says in the second bullet there, it's the interface between the parallel transmission of the computer bus and the serial transmission of the serial port. The most common Uart is a 16550 Uart, which has 16 bytes of on-chip buffer memory. And so that's quite a bit of memory, at least in modem communications. And it really helped to speed up the communications process too once they upgraded to the 16550 Uarts. I'm guessing that all of you are pretty familiar with USB, the Universal Serial Bus. It's pretty much replaced RS-232 in all of the serial communications, all but the most basic applications. Now RS-232 is still used a lot in, like I say, computer robotic environments and things of that nature, but as far as our standard computer system of the modern day, you pretty much are going to use USB as the standard serial port. It's considered to be a high-speed port. It's a multi-point serial communications technology, and it was developed to resolve a lot of the shortcomings that we had with RS-232. Currently there are two versions of USB. The original version was USB 1.1, and then the newer version, which is a higher speed, is USB 2.0. 2.0 is backwards compatible with USB 1.1. So if you have a 2.0 port, for instance, on your computer, you can still hook up a USB 1.1 device in that port. USB 1.1 was 1.5 megabits to 12 megabits per second, and USB 2.0 is theoretically rated at 480 megabits per second. And USB also supports up to 127 devices per host controller. In this graphic, we're taking a look at USB hubs. It's not quite as bad these days, but in the early days of USB, you were lucky if you got even 2 USB ports on your computer, and yet we had all these devices that were constantly coming out. They're all USB based that we needed to hook up to the USB ports on the computer, so you're always having to unplug and plug in another device. And so hubs helped out in that area quite a bit, because you can hook up a hub to a single USB port, and then you can attach a lot of your USB devices then to this hub, which had multiple USB ports on it. Now they have two types of hubs, the non-powered and the powered hubs. Non-powered didn't work real good, so I always recommend that if you're going to get a USB hub that you look into getting a powered hub. And so again, the idea is that we can have more devices connected to a single USB port on the computer, and it does give you the ability to extend to the distance that you have as far as reach, of the cable that you're hooking to that computer using a USB hub. These days we have all kinds of USB connectors. Originally they only had two types, the A connector and the B connector. The A connector was at one end of the cable, would plug into the PC, and the B end was at the other end of the cable, and that would connect to the peripheral device. Then with the 2.0 specification, they came out with the minis and the micros. On the far left there you see an 8-pin micro, and then just to the right of that you see a mini B. The mini B specification actually has been deprecated, meaning it won't be used in any new devices that are released. They're recommending that all new devices, the manufacturer of new devices, use the micros. And the other connector, if you look to the far right, we have an A, and then right next to that A, you see it says A receptor. So that's actually the female version of an A connector. An A connector is generally considered to be a male connector. But what the receptor does is allow you to have that connector on one end of a cable, so you can plug in the male end to it and actually create like an extension cord to extend the length of a USB cable. And then here in this graphic, we're just showing you the actual makeup of the pin structure of each of the different types of connectors that we looked at in the previous slide there. So we have the standard A and B, followed by the mini and the micro on the far right there, and then even the USB icon. Of course, that's something that we all recognize now as being the graphical indicator of the fact that a particular device is a USB-based device. And here's just a common example of different USB implementations. The graphic on the left is the USB ports that you would find in most computers, and then on the right, of course, that's a thumb drive and a USB connector there used to attach it to the computer. Here is a little bit more of an uncommon implementation of USB. This is the USB soldier here, and he's got all kinds of devices as part of his equipment that are USB based. If you look closely on the helmet on the far left there, he's got a USB camera. He also attached to the strap coming down to underneath his chin, the chin strap, he's got a USB microphone there, and more than likely he's probably got some sort of a transmitter that microphone is hooked up to and probably connected through a USB device. Where Isochronous Communications is concerned, you'll find IEEE 1394 usually implemented. Video cameras are a good example of that. They're very time specific, and so that's one of the big features of IEEE 1394 specification, is that it does have support for isochronous communications, which guarantees the data delivery at a constant predetermined rate. IEEE 1394 again is a high-speed serial solution, and it ranges from 400 megabits per second to 800 megabits per second and goes up to a distance of 100 meters. That was specified in 1394B. The constant data delivery rate reduces the need for a buffer, thereby greatly reducing the cost of implementing the technology. That's compared to our traditional asynchronous solution, which, remember, we're talking about the Uart and the modem previously. IEEE 1394 also has full duplex connectors. Remember what full duplex means. It can transmit and receive simultaneously, and it has 4-wire connectors as well as 6-wire connectors, which can also supply power to the devices. So here we see on the far left the yellow icon there, which represents the IEEE 1394 or FireWire. Of course, again, that's what you would see located on the ends of the cables or on the port on your computer to indicate that it's a FireWire port. In the middle graphic, the photograph there, you see the two different sizes of FireWire or IEEE 1394 connectors, and then you see a graphical representation of those on the far right hand side there. So you'll notice that the small connector is a 4-pin connector and the larger connector is a 6-pin connector. And so this is again a specification for electronic cabling and connectors that are used to connect multimedia devices like camcorders to PCs. And here again a graphic of a FireWire connector on the right, a 6-pin connector with the 6-pin port on the left there. So we should point out too that the connector on the right would be considered to be the male connector, and the port on the left would be the female connector. So that's it for our discussion of serial technologies. Now we're taking a look at parallel transmission technologies, and this is not really much in use anymore. Remember that the most commonly used parallel is still the ribbon cable that connects your motherboard to your hard drive. But externally on the computer, we used to use parallel cables to connect to printers and even scanners for a period of time. And they used a Db9 connector on one end, the end that connected to the computer, and then they had a 36-pin Centronics connector on the other end, and that was the end that connected to the scanner or connected to the printer. It was used commonly to connect, as I said, printers and scanners to PCs, replaced by USB, and the connector is no longer offered on new PCs. You can't even find a parallel port on your new PCs. So here we see a couple of pictures representing the Db9. The picture on the left there, that's the male cable that would plug into the female port on the PC. And then on the right hand side you see the Centronics parallel interface that was also considered to be a male connector that would connect to the female connector on the printer or on the scanner. And so that last slide was the end then of our wired data communications technologies. Now we're going to take a look at wireless technologies. There are two technologies that have been developed as wireless cable replacements: infrared or IRDA, and a radio wave based technology which is called Bluetooth. These technologies create for us what we call personal area networks. So if you've got a wireless mouse and a wireless keyboard that you use to communicate with your computer, or even maybe a wireless printer, then those peripheral components and the computer would make up your personal area network, or your PAN. First up then is IRDA, infrared. And infrared signals are point-to-point in nature. They have a narrow angle 30-degree cone, and they're limited to around a meter of distance, and they have a throughput, data throughput of 9600 bits per second up to 4 megabits per second. So it's not really a very high speed. It's again used mainly for peripheral devices, has been used for laptops to communicate with printers. But it's not very high speed. And the other drawback with infrared is that it's point-to-point in aspects of it, where you can't have something solid between the transmitting device and the receiving device. Whereas the next technology, Bluetooth, is radio wave based, and that's not as much of an issue in that technology. So Bluetooth is very popular wireless technology in all types of arenas these days, from using a headset to communicate with your cell phone. My cell phone actually communicates using Bluetooth with the sound system in my automobile, so that I don't even have to use one of these headsets. I can just be driving along and answer a phone call using a button on my dashboard, and just speak to a microphone that's also built into the dashboard to the person who's calling in, or maybe calling out to. So it's important to understand that Bluetooth is a radio frequency technology. One of the drawbacks of it is that it operates in the same spectrum, the 2.4 to 2.4835 gigahertz frequency spectrum, as does your Wi-Fi. So if you have the Wi-Fi on a laptop and you're also using Bluetooth for your keyboard and your mouse, they can actually cause interference with each other, which is kind of problematic. Also, another technology used with Bluetooth many times is called frequency hop spread spectrum, which is a technology of transmission. It's a way of actually encapsulating the data and then or encoding the data. If you remember in our previous chapter we talked about encoding data. And the big advantage with the frequency hop spread spectrum is that it does just that. It hops between frequencies, and so it makes it very difficult for somebody trying to intercept the communication between the devices. The data rate on Bluetooth is up to 1 megabit per second for a distance of about 10 meters. We don't generally use Bluetooth then for networking, although it is capable, the Bluetooth technology is capable of actually interoperating in a LAN-like mode where multiple devices can all interact with each other. But due to the slow speed, the 1 megabit per second, it's not outstanding for that particular purpose. But if you're just simply going to transfer a little bit of data from your cell phone to a laptop, or from one PDA to another PDA, or cell phone to cell phone for that matter, usually it's just a small amount of data, and so 1 megabit per second usually is fast enough to handle that. As I mentioned in the last slide, one of the key limitations of Bluetooth is the fact that it interferes with wireless LANs, with Wi-Fi. And security is an issue. Even though it uses the frequency hop spread spectrum, it still is a radio frequency transmission, and so it is susceptible to being intercepted. And then some of the devices that are on the market would be Bluetooth cellular phones, PDAs, headphones, mobile gaming platforms. On the right there in the picture, what you're seeing is a Bluetooth USB dongle. So this actually plugs into a USB port, and then you can use a Bluetooth mouse or a Bluetooth keyboard or some other Bluetooth device to interact with that computer that you plug the dongle into, if your computer doesn't have Bluetooth already enabled in it. Okay, moving on. Next we take a look at Internet Access Technologies. So we're talking about ISPs here, Internet Service Providers. The big guys, of course, the big players as far as ISPs are concerned these days are mainly our telecommunications companies, AT&T, Verizon, Sprint. America Online does still offer a dial-up service. In fact, there's a few companies out there that still offer a dial-up service for connection to the internet. Some of the things you want to consider when selecting an internet service provider would be the services that they offer you. They have additional services like web hosting, maybe mail, maybe data storage, things of that nature. Of course, performance and cost are probably the two things that most of us look at most closely when we're analyzing our decision, making our decision for what type of an ISP or which ISP we want to pay our monthly bill to. And then reliability used to be an issue. You don't find that to be too much of an issue with your internet service providers anymore, unless you're talking about using cellular communication, say on your laptop. Then you're going to find dead spots out there. But as far as home or business service goes, reliability not too much of an issue really these days. So primarily you'll probably look at performance and cost, but the different types of services they offer may be important to you as well. So here's the big picture as far as connecting to the internet is concerned. On the left-hand side is our consumer, which could be a home or a business, and they've got a computer that is utilizing either a USB or a FireWire serial communications method to connect to a modem, which in this example is a DSL modem or a cable modem. Of course, many of you these days might have UVerse or FiOS, which is a much higher speed service than is even cable or DSL. And so they're showing in this case here the modem being connected to the phone line, our local loop, you might remember. In this graphic here they also refer to it as the last mile, which is just another way to refer to the local loop, that connection between the business or the household and the central office of the telecommunications company. Now the actual first link that you're going to make would be the telecommunications company, and then they're going to forward it over to your ISP. Many times these days, again, they're one and the same, but you might have a third-party internet service provider. And so where you see the access server there, that would represent your ISP. That's the actual device then that's giving us access to the internet. And of course the pink cloud here is the internet cloud, and they're just showing you with that gray cloud there that there's all kinds of technologies that are interconnecting all the different systems that actually comprise the internet: T1s, frame relay, ATM, Metro Ethernet, And then down below, modem banks and DSLAMs, that's the Dsl Access Multiplexers, and then the cable system is the CMTS. Routers use the CSU DSU, which you also see there in the Internet cloud. So then again, on the right-hand side of the cloud, another access server, and this time it's the ISP for the corporate office there on the right. And so the terminology is still pretty the same. You know, it's the local loop, or the last mile is between, and they have it between the access server here. So there's two different access servers really. One would be the connection to the phone system. That's technically the building to the phone company's CO would be the last mile or the local loop. And then the phone company is going to forward that over to another access server, and that second access server would mean access to the internet as opposed to access to some other service that could be provided within this cloud here. So back then to the corporate office. The corporate office, you can see, is using a router, and so they would most likely, based on the fact that they're showing us in the pink cloud, CSU DSU, the router would also have that type of an interface, which is generally used to connect like T1 lines and T3 lines. They also would have just showing you a LAN there, a local area network that the router is attached to, and there's various devices attached to that LAN, including a server, which apparently is a web server for /.org, and so that makes up most of the components then that are the internet. You might notice that down at the bottom is this gray bar, and it says network protocols right above the bulleted items there, going between the consumer and the corporate office. So that's just indicating obviously that we have TCP/IP that's at the network layer operating. The individual networks, the local area networks, it would depend on what their network architecture is. On the corporate environment there, it says it's running LAN Ethernet, and so Ethernet would be the data link layer protocol that's being used. And in the home environment, more than likely that's going to be Ethernet as well. But then in the cloud, there's all kinds of different network data link layer protocols that could be utilized inside of there. And we don't really care what those are. As long as we can make the connection to our access server, that's really all we care about. And that's what all the bulleted points are. Is just here's the different possible access technologies that would be used here. So dial-up or a modem, some sort of a dedicated connection, meaning always on, something like DSL, Fios, UVerse, T1 lines or T3 lines. Somebody was telling me, and that's the note that I put out to the far right there, where I said up to 25 gigabits per second, that they use Fios, and that's the speed that they're getting on their downlink now, which is pretty incredible considering started out with a dial-up that did 300 kilobits per second. Cellular is also a possibility with little dongles that they plug into the USB ports. WiMAX, which is microwave technology, is also another possibility. And then, of course, Wi-Fi, the IEEE 802.11 specification. You'll find that a lot of cities now have set up hotspots in their downtown malls, and many coffee shops like Starbucks will have Wi-Fi in them, so you can be sitting there having a cup of coffee and accessing the internet, and airports as well. And I've experienced them at the airports, and I can tell you it's not free access, but they do provide wireless access in the airports. And of course, when you're at the college too, we also have wireless access for you as well. Now the rest of this chapter deals with modems, and so that's why you're seeing this graphic here, which is actually a flashback to our old one of our previous chapters, the public switch telephone network architecture. So real quick, we'll just go over this again, that PCs connect to modems, modems connect to the local loop connects us to the central office of the telecommunications company. The telecommunications company then, to get outside of their LATA, forwards their calls, transmissions, to a point of presence for a long distance carrier, also known as an inter-exchange carrier, or IXC. And then the IXC will forward to the appropriate LATA that we're trying to get connected to, and the POP that exists for them in that LATA. The POP again forwards over to the central office. Central office, using the local loop, heads to the modem, sends a transmission to the destination that we're trying to reach, and then the modem is connected to the remote PC there. So that could be just two friends communicating. That could be a person connecting to a web server. It could be a person trying to remote into their computer at their office. A lot of different scenarios here, but just again, really just a quick reminder of terminology that we had covered here previously that deals with the public switch telephone network. So we talked a while ago about circuit switch networks and packet switch networks, and this slide is really relating to the older analog networks. If you look under the PSTN cloud there, it says output input is analog, and that's not the case anymore. The phone system is all digitally based, and so pretty much you got packet switch networks going on in there. You don't have circuit switch networks anymore. But that's what this graphic was trying to imply, that we had the digital data in the PC coming out into the modem was converting it over to analog, forwarding it into the public switch telephone network, and it remained switched through the analog switches to come out the other side of the cloud, still in analog format. So the modem then had to convert it back to digital. It was then processed digitally by the ISP's router, which forwarded it in a digital fashion to the internet cloud. And so again, that's kind of older technology. As I say, it's pretty much all digital internally in the cloud these days. And for those of you using FiOS and UVerse, it's digital from your home into the cloud. It's only those of us that don't have access to those networks, who are still using DSL, that are still stuck in the old analog world here. I guess I can't complain too much. I could still be using a modem to connect to the internet, which is what we're going to take a look at here in the next few slides. So just a reminder again that the acronym, well, it's not really an acronym, the conjunction of modulation and demodulation is how we get the word modem. It's a contraction. There we go. And so again, they're claiming most local loops that are used for the PSTN connection are using dial-up phone service, and that they're two-wire circuits. Of course, that's not true anymore. And just tells you that in a two-wire circuit, one's the ground wire, the other is the one that carries the data. And then also within the transmission, there is the dial tone on the public switch telephone network, which is really the connection to their phone service. But you know, most of this doesn't apply anymore, but you're going to see some questions on the test about it, so we do have to go through it. So as Modem Technologies progressed, of course, we had all these different standards that, like anything else, is constantly changing. So we started out with the original Bell standards, then we had the V standards, and we also had, when we went to the 56 kilobit per second modems, there was what this slide refers to as the non-standards. Of course, this is now standardized, but there were two different standards that were both competing for the higher speed modem market at that time. And so one technology was X2, which was being developed by 3Com and US Robotics, and the other technology was called the K56 Flex, which was from Lucent Technologies, and that was the old Bell Labs before the breakup of the AT&T system, or I should say after the breakup of the AT&T system. The lab portion of AT&T became Lucent Technologies. So if you remember, again, back to a previous slide, long time ago, I think it was in the first chapter, we talked about how the fact that products, many times the technologies that are used in products are way ahead of the actual standards that are being released. And so I can actually remember buying a X2 modem from US Robotics and wondering whether or not that was going to be outdated or not when the actual standard was released. And the interesting thing at that time is that they actually would guarantee you that if their standard wasn't the one that was implemented, that they would actually, using firmware, they would actually give you a disk, I guess it was at that time, that we would be able to update the BIOS on the card, the adapter card, and switch from the X2 technology over to the K56 Flex technology. So anyway, we're going to go through and look at these the progression of these standards in modems. So in this table here, we just start in the bottom left-hand corner. You can see there's the first Bell standard, Bell 103, 300 bits per second. I think actually earlier I had said that it was kilobits per second. Now I look at this slide, I'm reminded that, yeah, it was only 300 bits per second, the first modems. Those were 300 baud as well. Remember that baud is the actual cycle of one wavelength. And we talked about the fact that there's technologies that we use to increase the number of bits that we can represent within a single baud. But at this time it was 1 bit per 1 baud. Then you move on to the Bell 212A standard. It was 1200 bits per second over 600 baud. So there we were using obviously 2 bits per baud. In fact, if you look in the far right column, you'll see there's the modulation methods that were being used. Frequency shift keying, and then the 4-phase shift keying. And then we got the V.22 bis. Bis is French, I believe it is, for 2. So version 2 of the V.22 specification was 2400 bits per second. It was also operating over 600 baud, so again what they did is they increased the number of bits per baud, and that's when the 4QAM and the trellis code modulation technologies were developed. And then you got the V.32 standard, 9.6 kilobits per second, the V.32 bis standard. And I should point out, I guess too, that starting with the V.22 bis, we also had data compression implemented and error correction technologies implemented. So you want to be familiar with the different types of data compression and error correction technologies too. There's a few questions in the quizzes and thereby on the midterm that'll be on that. So we left off the V.32 bis was 14.4K, V.32 TER, which is the third version, 19.2K, and then the V.34 gave us 28.8 kilobits per second. It was capable of going up to 33.6. And then finally we got to the V90 standard, which gave us 56 kilobits per second on the down and 28.8 on the up. Usually you download more data from the internet than you send out from your computer. You're just sending, short little bursts of request messages usually, and then you're downloading more information. So usually the downlink you're going to find in most cases, like DSL too, the downlink is usually more bandwidth dedicated to that than on the uplink. So you might remember we talked about full duplex and half duplex previously. And so just a reminder that full duplex allows for transmission in both directions simultaneously. And since we only have a 2-wire circuit in a phone system using a modem, one being the ground, one carrying the data, then you would probably assume that full duplex would not be possible on a 2-wire circuit. However, modems manufactured to the CCITT's V.32 standard and later, including the V.34 standard, can transmit in full duplex mode, thereby receiving and transmitting simultaneously over dial-up 2-wire circuits. So if you think about what that means, is that you are essentially doubling the speed of the transmission, being able to both send and receive simultaneously. Now you might also remember when we're using the analog network, we had digital data in the computer. It got converted using a modem to analog data, and then on the receiving end the analog data got converted back into digital. Well, that creates somewhat of a problem. It creates what they call quantization noise, and quantization noise is what occurs from that transfer, that translation process from digital to analog and then back to digital again. So that's what this graphic here is representing to you. You can see the original analog waveform, and now it's being sampled and converted to digital, and then you can see that there's the recreated analog waveform, and now they compare the original to the recreated analog waveform, and you can see there's these little gray areas down there, and that's the quantization noise. And so that causes errors in transmission. And so we're going to show you that that's one of the things that needed to be fixed when the V.90 specification came out in Modem Technology. Instead of converting it from digital to analog and then back from analog to digital, and then on the return too, it was, same thing, digital, analog. Anyway, both ends had that conversion going on when it was a fully analog network. So we're just going to show you that we had the conversion on one end, and then it was fully digital on the other end, and that was another way to help increase the transfer rates. Another thing that you want to be familiar with is that the theoretical limit of of the modern day phone lines is 56 kilobits per second. However, the Federal Communications Commission, the FCC, has actually placed a limit on that bandwidth, on the telephone network bandwidth, of 53 kilobits per second. And so here is the V.90 implementation in modems, and you're going to see here that the trick is we don't have as many conversions as we used to from analog to digital and back again, and so it reduces that problem of quantization noise and gives us more throughput. And it also, in this particular case, we had asymmetrical data transmission, which I guess we did see in that chart too. I was showing you that you had a higher speed on the downlink than you had on the uplink. Well, that's called asymmetrical, just like DSL is also asymmetrical data services link. So that just means it's not symmetrical. You don't have the same speed on your uplink as you have on your downlink. That's symmetrical. So if it's asymmetrical, you have one speed on the downlink and a different speed on the uplink. So in the V.90 implementation, you can see we have a V.90 modem on the far left here. So the same thing was going on here. You were taking from the digital PC, you were taking that digital data, converting it to analog, sending it into the phone system at the CO there over the local loop, which again is all analog at that point. But as soon as it hits the CO is taking that incoming analog signal, converting it back to digital, and so now it's digital from the local CO to the remote CO. The remote CO doesn't do any conversion. It keeps it digital where it sends it out now to the destination. So this would be the web server that you're trying to communicate with. So the company that's connected to the CO on the right hand side there, they're not using any kind of a modem. They're using completely 100% digital services there. So you can see it has the ISDN, Integrated Services Digital Network, or T1 as possible options there. It could be T3, could be other technologies, but those are digital services. So then from the web server, it's coming back the other way. It's going to be all digital into their local CO, no conversion again, digital back to our local CO. And so at this point in time, it does have to convert the digital back to analog, hands off the analog signal over the local loop to our modem, and then our modem converts it back to digital again. But we took out one conversion, the conversion on the right hand end there, out of the process, and so that has reduced considerably that quantization noise, gave us more throughput then over the public switch telephone network. So here's some tidbits of information on data compression. There's two different data compression technologies that were commonly used in modems, V.42 bis and the MNP class 5. The V.42 bis used the Lempel-Ziv algorithm, and it had a theoretical increase of throughput of 4-to-1 ratio, but through testing and whatnot, they determined that the reality was more like 2.5-to-1 as far as the compression ratio. In MNP class 5, there's actually two different algorithms that are being used, the Huffman encoding and the run length encoding. and the compression ratios here are about 1.3 to 1 and 2 to 1. And so just a reminder that another way to increase data throughput is through error prevention. So error prevention, remember, is preventing errors from occurring. And when errors occur, then the data is being misinterpreted due to noise or interference on the phone lines over which the data message has traveled. And that errors can be prevented by reducing the amount of noise or interference on a given transmission line, or by employing modulation techniques that are able to adapt and overcome noisy lines. And so that's pretty much something that's going to be dealt with on the telecommunications end, although within the modems they did employ the modulation techniques to help overcome the noisy lines and help to prevent errors from occurring. So for those of us that spent years experiencing modems, DSL was a godsend. DSL, the acronym is Digital Subscriber Line, and it was one of the faster broadband technologies available. Of course, these days it seems slow compared to Fios and Uverse. One of the big differences between DSL and phone modems is that DSL was an always-on connection. It's a dedicated connection, as is Fios and Uverse. And DSL, one of the big advantages from at least the telephone company's perspective, and the consumer too, because it was fairly inexpensive, was that it used the same copper wires that made up the local loop in the public switch telephone network. Also known as POTS, by the way, we haven't talked about that. That's plain old telephone service. Generally speaking, the POTS, POTS, is used to refer to the old analog system, and PSTN is used to refer to the new digital systems. So this graphic then shows you how DSL was able to work using existing phone lines in the frequencies that are available on the phone line. They were able to divide those frequencies up and divide it into 3 different areas. So voice is basically between 0 and 4 kilohertz. Then there's a 25 kilohertz guard band. Then there's an area of the frequency band that's dedicated to the upstream data. That's you sending information out to your ISP. And then another guard band from 100 to 110 kilohertz. And then at the very top there, from 110 kilohertz all the way up to 1.1 kilohertz, which is 1.1 gigahertz, I should say, 1100 kilohertz, is the downstream, meaning the data that's coming down into your network. And frequency division multiplexing, we talked about that back in an earlier chapter as well, so that's really what we're looking at here, right? Dividing the frequency and multiplexing, putting multiple signals on the wire simultaneously. And that's how DSL works. One of the problems with DSL is that it really isn't standardized, and so the different telecommunications companies really, each one had their own way of implementing DSL. So if you had a DSL modem from one company, it many times would not work with another company's DSL system. So the key is that your DSL modem needs to be using the same standard as the DSLAM, and the DSLAM is the Dsl Access Multiplexer. So that's the device that actually receives the signals from the DSL modems that are installed in the households and in the businesses. So the DSLAM is on the telecommunications side. And of course you can go out to Best Buy or electronic stores these days and buy your own DSL modems, but you do have to make sure that they will work with whatever telecommunications provider is providing the local loop services to your residence or your business. In the early days they did require you to rent the DSL modems or purchase them. Many times they'd charge as much as $150, $200 to actually purchase the DSL modem from them, and then they'd send one of their technicians out to install it for you. There's a lot of different flavors of DSL. ADSL is the one that we're most familiar with. That's the asymmetric DSL. But there's also IDSL, SDSL, HDSL, and VDSL. And if you take a look at page 104 in your book, you'll see that there's a table there, and it gives you a breakdown on all those other flavors of DSL. So here's a graphic representing the Dsl architecture. It has a PC connected directly to a DSL modem. Of course, a lot of these DSL modems have on the consumer side several ports so that you can connect several computers to that modem and have a local area network then on the consumer side. And then there's one port that is dedicated for the DSL link then to the telecommunications DSLAM. So again, remember that goes over the local loop. The DSLAM is the equipment at the central office of the phone company, and then the phone company will take the signal from the DSLAM and have it divided into one path that is the data that comes in from the computer there. It gets passed over and forwarded out through a router out to the internet, and then the other path is for the voice, is going to go into their phone switches, and the phone switch then makes the connection using or forwards the phone call through the PSTN cloud, the public switch telephone network, to whomever you might be calling. And so that's again, remember back to that multiplexing graphic, we had both the voice and the data simultaneously going over the local loop, and so that's what's being divided there at the DSLAM and split up to either the phone network or the data network, in this case the internet. Of course, another access technology is cable modems. This is also considered to be high bandwidth connectivity. Of course, cable companies provide television. Of course, these days telecommunications companies are providing television services as well. There was a time when that wasn't the case. But anyway, bandwidth not quite as high speed as your Fios and your Uverse, but much better than is DSL. That advantage came to the cable companies once they switched over finally to digital networks. They were analog for a long time. In the second bullet there, it's talking about the fact that the cable company's bandwidth is significantly higher than the service provided over the local loop. But again, remember, the local loop that they're referring to here is the old copper-based local loop, and many of you these days have fiber-based local loops. So this is not absolutely true. In fact, Fios and Uverse, as I said a moment ago, do offer higher speeds than does the cable company's system. So one of the advantages of using the cable company was that, again, they used to be the only providers of television, at least over landlines. We've always, not always, but for quite some time, we've had satellite communications, and of course we've also had the broadcast television networks. But this is showing the cable as it comes into your house, the fact that it could then be split and used for data purposes and used for TV purposes, transmission of video and audio as well. And so this graphic then is showing the cable system's data network. You can see on the right are the households and the businesses, and so they connect then to the various nodes that make up the network for the cable system, and those nodes then are connected by usually fiber these days. There was a time when they used coaxial cable to make the connection between those nodes as well. In fact, early days of cable, when they were analog, the big problem was the more subscribers that you had on a particular node, the more you were sharing the bandwidth, and so if your neighbors were all online the same time you were, then you had less bandwidth, to less access as far as data transmission was concerned to the internet or wherever you were connected to, maybe connected to your business. But once they went digital, then they were able to control that, so that's not an issue anymore. So you can see then that the cable networks then are connected through a distribution hub, and they also use the internet protocol on their networks over the underlying data link layers of SONET, ATM, or WDM. and then again making the connection to the internet, and they're showing in this particular case an OC12 link, which we'll talk about in another chapter, but that's the optical carrier link. You have the T services, which are copper-based, and the OC services, which are fiber-based. And so we'll get into that in a later chapter. Fixed point wireless is another access method. Fixed point meaning that there has to be an antenna, a receiver somewhere to pick up the signals from the wireless devices. So if you've got Wi-Fi in your laptop, for instance, you have to have some sort of an antenna to be able to receive those signals. With WiMAX, that's got to have a microwave receiver for that. And for cellular, of course, you'd have to have your cellular towers. So Wi-Fi, we're going to get into these in greater detail in later chapters. So just identifying support for all the different 802.11 specifications and speeds. And the same thing with cellular down below here, the different networks versions of cellular, 2.5G, 3G, and of course they're up to 4G now in the cellular networks.